Hello and welcome to this video on the octal number system. In one of our previous videos, we introduced the idea of the binary number system, and we talked about how we can convert between decimal numbers and binary numbers and back again. And in this video, we're going to do something very similar, but we're going to be looking at the octal number system instead. So just as a quick introduction to the octal system of numbers looks very much like the decimal numbers that we're already familiar with, but they're not the same, and there's some key differences. First of all, the oct in octal implies 8, like octagon having 8 sides. So the octal number system has only 8 digits, and these digits, I've put them down the side here, from 0 to 7. So be careful, it's not 0 to 8, we count 0 as a digit, so it's 0 to 7 in our octal system. And this number system historically has commonly been used in computing. The reason for this, which we'll see just in a second, is that the octal system of numbers gives us some efficiencies with the binary system of numbers, which is the system of numbers that computers use. So let's, for an example's sake, fill out this table very quickly and we'll see why that's the case. So on the top of my table here, I've listed some columns for our binary bits that are going to correspond with each of these octal numbers. And in our last video, we saw that our binary system of numbers is to the base of 2, and so the digits represent increasing powers of 2 each time. We start with 1s, then we have 2s, 4s, and we'd have 8s, 16s, and so on if we extended that. So let's fill out our table very quickly, because we can say that, first of all, the number 0, well, in a binary number, that would be 0, 0, 0, because our number is 0, so we want it all to add up to that. The next octal number is 1, so we have one lot of 1, we have no 2s and no 4s. Next, number 2, we'd have one lot of 2, but we'd have no 1s and no 4s. Number 3, we'd need a 2 and a 1 to make 3, but no 4s. 4, well, we have a column for our 4s with 0 in the others. 5, we need a 4 and a 1. 6, we need a 4 and a 2. And a 7, we need one of each. Now, the reason I'm doing this and mentioning the octal system in conjunction with the binary system is because the road ends here, as it were, because if we were to add, let's say, the number 8, we run into a bit of a problem. And the problem is that we'd need our extra column here of 8s. We'd need to say 1, 0, 0, 0 if we wanted to extend that pattern using the binary system. And so what's happened here is we need now an extra column. We need to extend the digits, or the bits rather, of our binary term just to accommodate these extra digits. Let's say we're in the decimal system, 8 and 9. And so the octal system rejects these two, because what we can do is, by rejecting these two, we can remove the need for that additional column and just have our 3 columns for the 1s, 2s and 4s as we saw. And that means that, let's think in the computer world, all of our processing, all of our data, which is held in terms of binary digits and binary bits, it means that all of our terms are now 3 bits in length rather than 4 bits in length. And so everything is 75% as large, as it were, and we save on 75% of our processing and our data and gain efficiencies in that way. So the octal system has largely been surpassed by another system of numbers called the hexadecimal system, which we're going to look at in later videos. But that's a kind of a little quick history there of why the octal system came about, and still is present in many applications, because it gives the efficiencies of only requiring 3 binary bits in correspondence with each of those octal numbers. That aside though, this video isn't going to focus so much on that, but rather how we can convert between octal numbers and other systems of numbers, such as binary or decimal. Let's start with some simple examples of how we can convert octal numbers into decimal numbers and back again. Let's start by trying to convert this octal number into a decimal number. So here we have the number 2564, and just to remind ourselves that it's an octal number, we've put the little base of 8 as a subscript next to it. And first thing you'll notice is that all of the digits in our octal number are the digits 0 to 7. We're not allowed to have the digits 8 or 9 in our actual number here. We're allowed the 8 as the subscript, obviously, just as a reminder for ourselves, but the actual number itself can only contain 0 to 7. The second thing is to avoid the temptation to read this number as 2564. The temptation is to do that because we're familiar with decimal numbers in everyday life, but what we're going to see in just a second is that this number is not 2564 when we express it as a decimal number. And so the way to do that is to expand this number in a similar manner that we did when we looked at the binary numbers in our previous video. If you haven't watched our video on binary numbers, it might be worth going back to have a look at that, because we'll talk about where this expansion comes from. But because it's an octal number, the octal system uses the base of 8 to construct the actual value of the number, with increasing powers of 8 as we move from the least significant digit to the most significant digit, going from right to left. So here we'd have a number raised to the power 0, to the power 1, to the power 2, to the power 3, and so forth. Again, if that doesn't make too much sense, then it might be worth going back to our previous video on binary numbers, where we talk about that in a bit more detail. But if we were to write this out in full, we'd have 2 times 8, because 8 is the base of our number. 8 to the power 3 was the rightmost one. Remember, it was 0, 1, 2, 3, going from right to left. So 2 times 8 to the power 3, plus 5 times 8 raised just to the power 2 now, plus 6 times 8 to the power 1, and plus 4 times 8 to the power 0. And when we calculate all of this, remember that 8 to the power 1 is just 8, and 8 to the power 0 is 1. Anything to the power 0 is 1. When we calculate that, we get our decimal result, which I'll just squeeze on the end here, as 1396, or 1396. And that's to the base 10 now. So I'll put a little 10 as our subscript. So you can see, hopefully now we've expanded that in full, that our octal number is not 2564 as we would be familiar in the decimal system. It's equivalent to 1396 if we want to express it as a decimal. Next, we're going to do the reverse process. We're going to try and convert our decimal number into an octal number. And we're going to use the same example here. So we have the advantage of, we know what the answer is going to be at the end, hopefully. But we're going to start with this number here, 1396, and convert that into this octal number again, hopefully. The way we're going to do that is by dividing our number by 8, and we're going to do that successively. We're going to do it over and over again, and each time we're going to take the remainder, and we'll see what we mean by that as we go through this example. So here's the first step of our example, and what you can see here is we've taken our decimal number 1396 and we've divided it by 8. And the result that we have here is 174 with remainder 4. So I want to pause here for a moment just to explain what it is that we've done, how you can do this for yourself. First of all, we're only interested in dividing our number by 8 to get an integer result. And chances are we're going to have to take a remainder out to do that. 1,396 divided by 8 doesn't give us a whole number result. We've had to take out a remainder, and the remainder we've taken out is 4. And so what we've really done here is 1,392 divided by 8, because we've taken 4 out in order to get that integer result. And so that's where our 174 remainder 4 comes from. Now, what that remainder is, or what the remainder should be that you take out, is not immediately apparent. You could do it by trial and error. The remainder will always be one of our octal digits, 0 through 7. I don't recommend doing a sort of trial and error approach with this. There's two options available to us here which are a little bit more reliable. The first one is, if you're on the internet, you can find what's called a modulo calculator, just by doing an internet search, and that will divide a number and give you the remainder. That's one option. If you're not on the internet but you have a decent sort of scientific calculator, you can get the result by using one of the functions on your calculator. So let's look at this particular division, 1,396 divided by 8, for example. If you plug that into a calculator, especially a modern calculator that has a fractional result, my calculator, for example, gives me 349 over 2 as a result. Now, on the calculator, hopefully, if you've got a decent scientific calculator, preferably a Casio, you'll have a function that looks like this. It's A, B over C between D over C. And that function there allows us to convert between the forms that our result appears in. And so what we have here, currently my result is in the sort of right-hand form there, D over C, one integer over another. I want to convert it into this form here. And so when I do that, I get, let's just write this down, I get 174 and a half. Now, the reason that this is useful in finding our remainder is because 174 was obviously our integer, which we're interested in. The fraction that we have left over here in this mixed number is a clue as to what our remainder is going to be. The only thing to remember is that we divided by 8. And so here we need to multiply this leftover fraction by 8 in order to find the remainder. And so here we had a half, and a half multiplied by 8 again gives us 4. And so there's a couple of ways of finding the remainder effectively for our division. Let's carry on and repeat the step. We're going to do this several times. We're going to take our integer from the previous step, which was 174. We're going to divide it by 8 again. So we have 174 divided by 8, and this time that's going to give us 21 with remainder 6. What I'm going to start doing as we go down here is start to construct our octal number, and we're going to do that from right to left, from the least significant to the most significant. And so we start with our 4, which was our first remainder there. I'll just put this down in the bottom right hand corner. So 4 was our first remainder. That's going to be our least significant digit. And we're going to add the 6, which is the next digit to the left. Let's carry on our process, because we now have 21, which was our last integer, divided by 8 again. And that is going to give me 2 with remainder 5. Remember, it's the remainders that form our octal number. And so the next number there being 5, we're going to add that to our result. The last step is to say 2 divided by 8, because 2 was our last integer there. Well, 2 doesn't divide by 8 to give us an integer number no matter what remainder we take out. There's no way we can divide 2 by 8 and possibly get an integer as a result. And so our last digit is simply going to be 2, and that's going to be on our octal number as well. So there we've done the reverse process. We've taken our decimal number of 1396 and we've converted it back to 2564, and that's to the base of 8, remember, as an octal number. So in the last example there, we were dealing with whole number integers converting between decimal and octal. Let's have a look at another example here where we have a number that is after the decimal point, as it were, 0.4375 to the base 10. So it's a decimal number, and we want to convert this into an octal number. Well, if you watched our video on binary numbers, we saw that the process was very similar, but the opposite. And we're going to do something very similar here when converting to octal. So rather than dividing by 8 each time, we're going to multiply by 8 each time. And we'll see how that process works to build up our octal number. So first thing we're going to do is we're going to multiply by 8. And when we multiply 0.4375 by 8, we get a result of 3.5. And the number that I'm interested in here is the number before the decimal point. In that case, it's 3. And so 3 is going to form the first digit of our octal number. And we're going to build our octal number from left to right now after the decimal point. So we'll build our octal number on the right hand side here. We'll start with the decimal point, and the first digit of our octal number is going to be 3. So we've got 0.3 so far. Now imagine that we've kind of removed this 3 in order to form the first digit of our octal number. So we're left with 0.5 or 0.5 as it were. And so next we're going to multiply 0.5 by 8. So again, multiplying by 8, 0.5 times 8 gives us 4 or 4.0. And so 4, again, I'm interested in the number before the decimal point. So 4 is going to be the next digit of our octal number. So 0.34 we have now. Now that we've removed that 4, we see that we're left with 0. And so there's no remainder, and our conversion is complete. So what we've said is that 0.4375 to the base 10 is equal to 0.34 to the base of 8. One of the big advantages of octal numbers is that they're very easy to convert into binary numbers and back again. So let's have a look at the same example that we just found on the previous page there, where we found 0.34 to the base of 8, our octal number. And let's say that we want to convert that into a binary number. It's very easy to do just by referring to the table that we produced at the very beginning of this video. So we see that the decimal 3 is listed here and corresponds with 0, 1, 1, our binary bits. And so what I can do is I can start to construct my binary number. It's going to be 0. Well, our 3 is represented by 0, 1, 1. And that's followed by the number 4. And we see that the number 4 as an octal number is represented by 1, 0, 0. And so I can add on 1, 0, 0 to my term there. The one thing that I can do here is trim from the end of the number these two zeros that are unnecessary, really. We can just strike those through like so, or just erase them altogether. So what we can say is that our number 0.34 to the base of 8 is equivalent to 0.0111 to the base of 2, because that's a binary number now. Earlier on in this video, we found this octal number, 2564 to the base of 8, and again, we can easily convert that into a binary number. The number 2 corresponds with 0, 1, 0 as a binary number. 5 is given by 1, 0, 1. 6 is given by 1, 1, 0. And 4 is given by 1, 0, 0. You can imagine that the decimal point would be at the end of this number here, so we're not allowed to trim numbers from the right-hand side where they'd be adjacent to the decimal point here, because that would change the value of the number. But I can trim zeros from the very beginning, and so there's 1 0 here which is unnecessary and we could remove if we wanted to. So one of the big advantages of this is octal numbers are often used as a stepping stone to reach binary numbers, because if we were to convert this number into a binary number, for those who've seen our video on converting to binary numbers, this would have taken lots of steps of dividing by 2 each time to get digit by digit this long binary term. That would have been quite a laborious process, but what we did in this video is we found this octal number just by dividing through using 4 steps, dividing by 8 each time to reach these 4 digits, and then it's much easier to convert these 4 digits into a binary number as shown. And so we can often save a bit of time and effort if we have to convert a decimal number into a binary number. First convert that decimal into an octal number, and then convert that octal number into a binary number. Let's have a look at one final example of the reverse process. So here we have a binary number, and let's say that we want to convert this into an octal number. Well, we can see here in our table that all of our octal numbers are represented by 3-bit binary combinations. And so all we're going to do is we're going to group our number here into groups of 3. And we're going to start from the decimal point, moving to the left and to the right. So starting by moving to the left first of all, we can see here, I'll mark these on as well, we've got the number 101, that's a group of 3, and then we've got the number 011 as a group of 3. But here we run into a problem, because at the end we've got this 10, and it's obviously not a group of 3, we've only got 2 digits at the end there. And why is that? Well, it's simply because someone has trimmed the 0 from the start already. So we can just add that on. So actually, our last 3-digit combination is 010. So referring to our table, 010 is 2, 011 is 3, and 101 is 5. So we have 235. On the right-hand side, again, we have the same problem. We've only got 10 there. And so we can simply pad out our number with some extra zeros to make it a 3-digit combination. So we've got 100 there, which is 4. I'm not forgetting that point there. So our number, our binary number to the base of 2 there is equal to 235.4 to the base of 8. Just remember that you're only allowed to add these additional zeros on the right-hand side after the decimal point at the very end of the number, or if it's before the decimal point on the very left-hand side at the very beginning of the number. That's the only two times where you can add extra zeros without changing the value of the number. So I hope you found this video useful. First of all, as an introduction to the octal number system and how we can convert between decimal, ordinary numbers and octal numbers and back again. But also at the end here, how we can convert between octal numbers and binary numbers, which is much easier than converting from a decimal number to a binary number. And for that reason, octal numbers often being used as a kind of stepping stone to do so.